When solving a physics problem, selecting the coordinate system is a very important way to help really simplify a problem. So we're going to talk about two types of things. The first one to talk about is something going down a slope, like this. And you're always going to want to pick it so your coordinate system is not. You don't want to do this. You just don't want to pick the general coordinates. You always want to pick it so that x is along the slope and y is perpendicular to the slope. And we're going to talk about why. So there's my system. I'm going to have this mass going down the system. I'm going to put my coordinate system attached to the Earth. It's looking at that spot right here where it starts. So there it is. And if I draw my phi-body diagram, I'm going to have, and it's important always to draw the forces exactly where they're located. So gravitational forces act at the center of the mass, so you draw it at the center of the mass going down, mg. The frictional force, and then I'm assuming I have some force between the acting on the mass from the ground, I draw it at that interface, right at the center here. Okay, I'll call that normal force. And then I might have some frictional force, for example. I don't know what it is, but I'll draw it there. I'm going to draw it at the interface in the direction it is showing. Okay, I'm going to pick this coordinate system I said, but I'm always going to pick that way for something on a slope, and we're going to understand why. We want to try to change this problem as much as we can from a two-dimensional problem to a one-dimensional problem, and picking this helps us do that. So if I just redraw this free body diagram, I can do that. So here's redrawn, and I'm going to try to draw every single force as its components either in the x direction or the y direction. I'm not going to draw any force that's not either x or y. So the normal force is already in y, so that's good. The frictional force already is in x, that's good. This magnetic force is not aligned with one of these vectorial directions. It has some components that are, but so we're going to break that up and so it matches that. So if I think about it, here's my force down. That's really it's this plus that. So there is some force in the minus y direction, which is magnitude mg cosine theta. So I'm going to draw that here, mg cosine theta. Okay, and then there's some part of this force that's moving it in the positive x direction, and that's mg sine theta. So I'm going to put mg sine theta in there. So I just redrew those, and I put this is the exact same thing as that, just showing it vectorially, and that's going to help me when I do my net forces. So now my net force is acting on it. I'm going to consider this is my positive I direction in that direction. So everything this way is going to be called positive because that's my positive. Okay. So this frictional force is in the minus direction. So it's a minus frictional force in the I direction. And this component of the gravitational force is in the plus direction, mg sine theta. So those are all my I forces. And then my j forces, that's my positive j. Is this positive, this going up this way? Fn is positive direction, so that's a positive force in the j. In this part, mg cosine theta is is a negative j. So those are my net forces on there. And so why is that important to break this up this way? So one thing you think about is like momentum. If I think about momentum is a vectorial quantity, so I think about the change in the momentum in this to the y direction first equals the net forces in their y direction times the dt. Well, the change in the momentum in the y direction, that's so this thing we'll assume this is constant mass. That's the mass times the change in the velocity of the center mass in the y direction. here's what I call the y direction. It was up and down. Is this mass, when it's sliding on this thing, on the slope, does it have any change in velocity in the y direction? No, it's not. It's relative to the y direction. It has no motion up and down relative to the y direction. It's all the motion is in the x direction. So I know this goes to 0. So now I know 0 is the F net of y. So that right away that helps me that I can use. So I know this is F net in the y direction. So I know Fn. So 0 equals Fn minus mg cosine theta. So Fn is mg cosine of theta. So I got Fn, relation between Fm and mg, without even really have to worry about things, because I know there's no change in momentum in the y direction. So now that's helpful for the future, because now when I do the change the momentum in the x direction, which I know it's going to have something, I can do the F net in the x direction dt, and I just can get that from here. If I want to think about work too, I can do it. So work is, in general, F dot dr from the initial to the final state. In this condition, since thetas aren't changing, nothing's changing, the force magnitude is constant, so this can come out of the integral sign. So it's just the force times the change in the r, which is the force in the x direction change times change in x directions, because it's a dot product. So just the forces, and then the force in the y direction times the change in the y, etc. Well, the force of x is this term. These are the forces acting in the x direction. These are all the forces acting in the y direction. And we know delta y is 0. So this goes to 0. So we know these terms are 0. The only work we're going to get is because it has to be work in the direction of motion, which is, now we simplify down to x. So therefore, the only things you have to worry about as far as making work are these forces. So we think about the force, work done by the frictional force. So that's the frictional force. And this is minus times delta x. If I say start from the top, went to the bottom, and this is sine theta, we know the relationship between h and delta x gives me, this is what delta x is, h over sine of theta. So this one travels h over sine of theta. Is how far each of these forces travel. So that force travels this far, so that's the value. And let's check it. The force is in this direction and the motion is this direction, so that work is negative on this thing. And then for gravity, we're going to have the force. So this term f of x here, mg sine of theta, times delta x, which delta x is this. So I just put in delta x, and I get these sine of thetas cross out. I get the work done by gravity is mgh, which is, well, it's positive. So that's the first check, because force is, gravity is down and moves down, so that's positive. And you expect the work done by gravity, I think, is always mgh. So that works. And so that's why this is useful, to help break it that way.